Hi everyone, in this video we will introduce our exploration algorithm, two-stage viewpoint planner. This is also the work in our 2021 IROS paper. First, why do we do exploration and what is the problem of exploration? In many search and rescue tasks, people need to work in really dangerous environments like the ruins after a nuclear disaster or an earthquake. If we can send a robot into this case and let it search the environments autonomously, then people don't need to take the risk to work in it. And also, if we make the exploration efficiently, it could help shorten the time of search and rescue. But an environment with convoluted and complex structures like the figures is still a big challenge for exploration. So we want to make an algorithm that can handle these environments. There have been some work on this topic. Most of them can be divided into three types. The first type is frontier-based algorithm, which is also the earliest method proposed to solve the autonomous exploration issue. The second type is algorithm based on learning, but they are still in development and not able to be applied in real life temporarily. The last type we call next best view algorithm. They are mostly based on RT or RG. Three latest algorithms of this type are Next Best View Planner, Graph-based Planner, and Motion Primitive-based Exploration Planner. Our work also draws inspiration from this kind of algorithm, so we are going to introduce more of them. Most existing Next Best View algorithms have the same drawbacks when applied to real life. First, they do not consider the existing viewpoints when building new RT or RG in each iteration. The problem to do so is waste much computation on some repetitive viewpoints. Second, every time when they do the global plan, they need to calculate the gain of all unvisited viewpoints again, which needs much longer time as well as more computation. Third, most of these methods depend on a random sampled viewpoint to find unexplored area. This is not reliable, especially when there are narrow openings. If the RT or RG cannot expand into those areas, then the exploration will ignore them. The last drawback is the back and forth behaviors like the figure shows. This happens a lot and decreases the overall efficiency. So we make our own method to solve these issues. Our planner includes two stages. In the first stage, the planner expands RT and keeps guiding the robot to new areas, so we call it exploration stage. Then the second stage, the planner relocates the robot to another unexplored area with global frontiers, so it is called relocation stage. In exploration stage, we keep those useful viewpoints from old tree in each iteration and reconstruct the whole tree. In relocation stage, frontiers are used to guide the relocation without caring about the gain of those viewpoints. Both changes help save much computation in each stage. We maintain the update of frontiers in both stages to make sure all areas are covered or recorded by the planner. In addition of these theoretical contributions, we release a benchmark environment. Anybody can use this environment to assess their development on exploration or navigation. Here is the detailed process of the exploration stage. The figure in the left includes information from the previous iteration. RT are expanded in free space inside the planning horizon. After that, a path is planned from A to B. It is obvious that most viewpoints in the first figure are in the middle of the horizon and cannot see any new information. If we remove all of them and reassemble new viewpoints, it won't make the planning better, but just occupy more computation. So the best way is to keep those viewpoints that are inside the new planning horizon. From the second figure, the number of new sampled viewpoints is less than half of the overall number. That means the computation is almost half. We hope more viewpoints could be sampled around the frontiers, but not uniformly distributed in the space. So local frontiers are also used to guide the expansions of RT. This also helps to speed up the planning in exploration stage. Our principle in relocation stage is to choose a viewpoint that is able to observe the closest global frontier best. So first, we select the closest frontier that can be observed by any viewpoint. In this figure, point B is the first selected viewpoint that can observe the selected frontier. In our method, if point A and point B are both able to observe the frontier, then the closer the better. Thus, we select another closer viewpoint A as a relocation point. We conduct simulation experiment with our benchmark environment in 3 scenarios: indoor, garage, and campus. Here we run the open source code of NBVP, GBP, and MBP as comparison. In each environment, we run each method 10 times and then calculate the average efficiency. The trajectories in the figure is the best one of each method. From the trajectories, all the other 3 methods have a lot of back and forth behaviors, especially in the garage, a multi-level environment. The table shows the efficiency of each method. It is obvious that our method almost 2 times as efficient as the others. In the table, we list the average planning time of all iterations of each method. Our method's planning time is nearly half of the other methods, and CPU load is the lowest in the whole round. We also conduct an environment in real platform at the campus of CMU. Our platform includes a well-done 16 LiDAR, a camera, and an IMU to do the localization and mapping. The right figure includes the trajectories of all methods. Our trajectory covers all areas and never goes back and forth. Only MBP can cover all areas, but still have some back and forth in some open area, like the right bottom corner. GBP missed one area in the left bottom, and NBVP has the most back and forth behaviors and missed many parts of the map. From the figures, we can easily tell that MBP has the best performance among all other 3 methods, even though it still spends double time of ours. In the experiment, our method has the most stable and shortest planning time. MBP and GBP both have some sharp increase when they are doing global plan. According to the second figure, our method almost has no stop in the whole process, which is impossible for other methods because of their longer planning time. Here is a video of our experiment. Here we show the switch between exploration stage and relocation stage, when there is no local frontiers in exploration stage, and then it will switch to the relocation stage by itself. Relocate the robot to a viewpoint that can see a global frontier. This is the whole process of our exploration planner. The planner explores almost all areas that it is supposed to. This is the trajectory and the map our exploration planner built. The robot travels 993 meters in 70 minutes. We release a benchmark environment in this paper. All our simulations are conducted in this environment. You can both get our open source code of DSVP and the benchmark environment in our website, cmuexploration.com. Thanks.